Hello class, today we are going to begin with an entry problem. This is on your guided notes. If you wouldn't mind pausing the video right now so you can work on the entry problem, and then I will go over the solutions. So this first set of problems asks you to change the angle from degrees to radians. So we learned yesterday that 180 degrees equals pi radians. And so what we can do is multiply by that conversion factor, and you'd have to put pi on top and 180 on the bottom so that the degrees cancel. So here I get degrees over degrees, those cancel. And then if I multiply across, I get negative 250 over 180 pi. And then all that is left to do is I have to reduce that fraction. So I could divide top and bottom by 10, and I get negative 25 pi over 18. I don't believe there's any other common factor because 25 is just 5 squared. So this is going to be all reduced. So that is negative 250 degrees in radians. To switch 6 degrees over to radians, again, I'm going to multiply that by pi over 180 degrees. The 180 degrees has to go in the denominator so that the degrees will cancel. So the degrees cancels there. And so then I get, multiplying across, I can put this over 1 if I want to. I get 6 pi over 180. And those are both divisible by 6. So if I divide the top and bottom by 6, I get pi over 30 radians. Now this next part has me evaluate sine of pi over 4. So I believe probably the most straightforward way to handle this is to consider what 3 pi over 4 is in degrees. Yesterday we learned that pi over 4 radians is 45 degrees. So here we have 3 pi's over 4. So we have 3 times 45 degrees. So again, pi over 4 is 45 degrees. And if I have 3 over pi over 4, I have 3 of those. So 3 times 45 degrees is 135 degrees. When I go to check out the unit circle, I know it's going to be in the second quadrant. I know that if I rotate 135 degrees, my reference angle is going to be 45 degrees, because 45 degrees is how much more I need to get a full 180 to get all the way down to the x-axis. I can drop my line down to the x-axis. Here's my right angle. I can see that I have a 45, 45, 90 right triangle, which means both of the sides that are not the hypotenuse are going to be radical 2 over 2. And when I consider my journey to my point, I have to go left to line up with my point and then up to line up with my point. Left is a negative, so it's going to be negative square root 2 over 2. We know sine is opposite over hypotenuse. So the opposite side is radical 2 over 2. The hypotenuse is just 1. So it's radical 2 over 2 over 1. Next, if I'm considering cotangent of 11 pi over 6, I'm going to consider how many degrees 11 pi over 6 is. So let's consider the pi over 6 part of 11 pi over 6. Pi over 6 is 30 degrees. We talked about that yesterday. 11 pi over 6 is the same as 11 times 30 degrees. So what we get is 330 degrees is the angle in degrees that we're looking at. So if I consider the unit circle, I'm going to be in the the fourth quadrant. Here's 30 degrees right in here, but I want to zoom in 30 degrees. Try my side up. Here's my right angle. I know across from the 30 is a half. And since I went down, it is negative a half. And then the other side is radical 3 over 2. That one is a positive quantity. Cotan of any angle is adjacent over opposite. It's also x over y. So the cotan of 11 pi over 6 is going to be, and when I look at adjacent, the adjacent side that isn't the hypotenuse is this one right here, that radical 3 over 2. Over the opposite side is all the way across the angle to that side. That's that negative 1/2. We know that dividing is the same as multiplying by the reciprocal. So this is the same as radical 3 over 2 times 2 over negative 1. Taking the reciprocal of that denominator, the 2's cancel, and radical 3 divided by negative 1 is negative radical 3. So that is the cotan of 11 pi over 6. So that was a little review of what we did yesterday. Now we're going to focus on two topics: arc length and sector area. The arc length is a length around a portion of a circle. So if we consider a circle of radius 4 rotated 2 pi over 3. 2 pi over 3, we can consider this in terms of degrees or radians. I'm just going to try and keep it in terms of radians. 2 pi over 3, this is pi over 2, and I'm a little beyond that 2 pi over 3. Let me try and redo that. 2 pi over 3 is about right here. And so what I want to know is if the circle is 4 inches with a radius of 4 inches, what would be the length of this portion that I have highlighted in green? That is the arc length of the circle. And then this angle is 2 pi over 3. That is how far I rotated. And again, if you're having difficulty thinking of this in terms of radians, you can always switch it over to degrees. 2 pi over 3, a pi over 3 is 60 degrees. 2 pi over 3 is twice that, so that's 120 degrees. So we're at 120 degrees, which is approximately what I drew out right there. So I want to know, what is the length of the intercepted arc? That is what I have highlighted here in green. So what I like to do is first show how to do this without using a formula. And then I'm going to show you what the formula is. So therefore, if you are in a math placement test or somewhere where you can't just Google the formula, you can come up with it on your own. Consider that to go all the way around the circle is the circumference of the circle. And the circumference is found by doing 2 times pi times r. So the circumference all the way around is 2 times pi times 4. So it is 8 pi to get you all the way around this circle. So it's a little over 24 units going all the way around, because pi is a little over 3. So 24 units to go all the way around the circle. So this is the whole circle. But you are only doing a portion of that circle. You're walking around a fraction of the way, kind of around the circle, but not the whole way around. If I went the whole way around, it would be 8 pi. We're doing a portion of the way around the circle. So we have to figure out what fraction of the way are we going around. So you can consider that question in degrees or in radians. If you're more comfortable in degrees, you'd say, I am going 120 degrees out of a full 360. That's the fraction I'm going. Or you could do it in radians. You can say, I'm going 2 pi's over 3 over 2 pi. Because 2 pi is a whole circle, 360 is a whole circle. This is the fraction of the way I am going. So I am going, either of these would reduce to 1/3. 1/3 of the way around the circle. Okay, which makes sense with our picture. It's about, approximately 1/3. If we consider it like a pizza, it's 1/3 of a pizza. Here I could reduce this to 1/3, 2 pi over 3 times the reciprocal of the denominator, 1 over 2 pi. The 2 pi's cancel, so you get 1/3 of the way around the circle. For this fraction, you get it by just reducing that fraction. But we're going 1/3 of the way around the circle. So a whole circle is 8 pi. You're going 1/3 of the way around the circle, so you're going 1/3 of 8 pi. So in other words, 1/3 times 8 pi is the fraction of the circle you're covering times the whole circle. So your arc is 8 pi over 3. Arc length is 8 pi over 3. So that is this length. It's 8 pi's over 3. So this is kind of the hard way, but to me it makes sense. You find the fraction of the way you're going around the circle times how much it is to go around the whole circle. So if I'm in a situation where I don't have the formula at the tip of my fingers, or I can't remember it, I can just do this calculation. Now here is the equation that is actually very straightforward. The only caveat here to calculate arc length is always given as S, is that you have to have your angles in radians. So S, the arc length, is just the radius times the radian measure of the angle that you're carving that arc length with. So S equals r theta. So it says, given a central angle of 25 degrees, find the length of the intercepted arc in a circle of radius 7 centimeters. So 125 degrees, you're about here. 125 degrees. I want to know the length of this arc right here. If I'm using the formula, arc length equals r theta. Theta has to be in radians. So I'm going to take 125 degrees times pi over 180 to get theta into radians. So I get my degrees to cancel. So it's 125 over 180 pi. And first thing I'm going to do is divide the top and bottom by 5 just to reduce, and then if I can reduce more, I will. If I divide the top by 5, I get 25 the bottom by 5, I get 36. So I get 25/36 pi is theta. We know r is 7 because it's given to us. So arc length is going to be 7 centimeters times 25 pi over 36. Now, if I am doing this for a real life, like maybe I'm designing a garden or I have some sort of round feature in my house, I would just use approximately 3.14 for pi and do that particular multiplication. If it's pure math, I can just leave it with the pi in it. So I get 175 pi over 36 centimeters. And that is the length of our arc. I'm just going to calculate it in terms of what it would be not in pi. It's approximately 15.27 centimeters. So that is the length of that green highlighted part. So really either is acceptable, but if I'm doing a math problem that's pure math, not set in a real life situation, leaving the pi makes it more exact. Okay, so next we have the concept of area of a sector. So a sector is basically like, if I think of a whole unit circle is like a pizza, we're cutting out a slice of that pizza and we're considering the area of that pizza slice. So here it says consider an angle of pi over 3. So that's going to be 60 degrees. We know 60 is in the first quadrant, so I'm going to say about right here. If the radius is 5 centimeters, what's the area of the sector? I want to know the area of this part of it. If this is 60 degrees right here. So if I don't have a formula in front of me, I can just kind of do some logic to figure it out. I know the area of the whole circle is pi times the radius squared. So I know the whole area is 25 pi. Now I have to consider what fraction of the circle am I considering? So what fraction of the circle is pi over 3? So you can consider this two ways. It is 60 out of 360 degrees, 360 being the entire circle, or you could say it's pi over 3 out of 2 pi radians. So if you want to deal with degrees, you can do that. If you want to deal with radians, you can do the second one. So dividing both sides by 60, I get 1/6 is the fraction of the circle. Here I would multiply pi over 3 times the reciprocal of the denominator, 1 over 2 pi. So we can see there that the pi's cancel. I can multiply across, it's 1 over 6. So either way, the fraction of the circle is it's 1/6 of the circle is the area we're considering. So it's 1/6 of 25 pi, 1/6 of the whole area. So we know of means multiply. So what I get is 25 pi over 6 centimeters squared, because area is a squared length quantity. So multiplying across, I get 25 pi over 6. And again, if it was a real problem, I would just calculate that in terms of pi being approximately 3.14. So that is kind of the long way to do it, and that's how I'll do it if I don't remember the formula or don't have access to look it up. There is a formula. It is kind of a cute formula, but again, theta has to be in radians. And theta being in radians really simplifies the formula, but it does add some extra work if the problem is not given as an angle in radians. So the example says find the sector area. The radius is 3 inches. The central angle is 240. So they're just saying you're rotating 240 degrees from my initial ray. So here to 240, I'm in this quadrant here, the third quadrant, and I'm finding the area of this much pizza or pie or whatever you want to do to create an analogy there. So first thing I like to do is have theta go to radians. So theta is 240 times pi over 180. Again, we have 180 in the denominator so that those degrees cancel. So I'm going to reduce the fraction. I get 240 pi over 180. Initially, to reduce, I'm going to divide by 10. So I get 24/18 pi. And then I know 6 goes into each of these. I think 6 is the highest. So if you divide top and bottom by 6, I get 4 pi over 3. And so my formula, the area of a sector is 1/2 r squared theta. So r is 3. Theta is 4 pi over 3. So one of those 3's can cancel. So this can cancel, this can cancel. And if I multiply across, I get 12 pi over 2. 12 pi over 2 is just 6 pi square inches. Because when I square 3 inches, I get a unit of inches squared. So now you will have some time to work on arc length and sector area.